Hi guys, thanks for tuning in. My name is Evan Green. I'm a graduate student here at the University of Buffalo. I'm working with Dr. Chris Lowry, my advisor, and Dr. Elizabeth Thomas, both faculty members here at University of Buffalo. So today I'm going to be presenting the progress I've made on my research thesis project, which is titled Creation of a Coupled Groundwater-Surface Water Flow Modeling Approach, driven by regional climate models for assessing the impact of climate change on the hydrologic system. So my research goal is to produce an innovative three-part modeling approach for quantifying the impacts of climate change on groundwater and surface water flow regimes. So as many of us know, climate change is a prevailing issue that may lead to many different hydrologic challenges that we'll need to address in the future. However, to date, little effort has been made for coupling a model that covers the entire hydrologic system from climate, surface, and groundwater flow models. So what we need is an efficient and effective method for forecasting these changes. That way we can assist stakeholders in addressing these challenges. So to fill this knowledge gap, I produced a coupled groundwater surface water flow model of Western New York using the SWAT-MODFLOW method, which is linked in each time step to a suite of regional climate models. So model outputs will include groundwater flux, stream discharge, hydrologic head, and river stage. And time permitting, we hope to incorporate an RT3D model, which will be later embedded in the framework of the MODFLOW model. And that way we can forecast nutrient fluxes, specifically nitrogen fluxes, in groundwater and surface water in relation to climate change. So the climate models that we're using predict a 3.6 degrees Celsius increase in mean temperature by 2070, the end of our modeling time period. Over that corresponding time period, we see a 15% increase in annual precipitation, with a greater increase in winter months relative to the other months. We see an increased variability in daily and seasonal temperatures and precipitation. And finally, and perhaps most importantly, for my model, we see an increased frequency intensity of precipitation events moving into the future. So my model domain incorporates the Buffalo River watershed up here, centered around the city of Buffalo in Western New York. Our model domain includes urban, rural, and agricultural lands, so that we can see how the varying land types will be affected by climate change in the future. So this modeling approach will assess groundwater and surface water quality and quantity, and assess expected hydrologic issues for this region in relation to climate change. Specifically, what I'll be using the outputs of my model for are assess the frequency of combined sewer overflows in the future, as well as assess the frequency of groundwater flooding due to increased precipitation in the future. And later we hope to be able to forecast nitrogen discharge from the Buffalo River watershed into Lake Erie, and this represents a really important first step in predicting the prevalence of algal blooms in the future under a changing climate. So we'll be using a three-part modeling approach, which connects all portions of the hydrologic system in Western New York. Initially, we'll be calibrating to historical data for the time period of 2005 to 2015. Once we feel that the model is properly calibrated, we're projecting forward for two time periods, 2045 to 2050 and 2065 to 2070. So we'll be using three regional climate models, which will drive the model in each time step. And these will be linked in each time step to the precipitation component in SWAT. The SWAT-MODFLOW method works such that MODFLOW replaces the SWAT groundwater component and is embedded in the subroutine within SWAT. Hydrologic response units, HRUs, which are a component in SWAT, which is a discrete combination of land use, soil type, and slope, are really what are going to be facilitating the movement of water between these two models. So water can be exchanged between the two models in four different ways. We can move water from SWAT, the surface water component, to the groundwater component MODFLOW as net recharge and as stream loss in the stream channels. And then conversely, we can have water move from MODFLOW back into SWAT as base flow in the channels or as evapotranspiration. So SWAT-MODFLOW is really going to be calibrated externally because SWAT-MODFLOW doesn't have a calibration component quite yet. So we're using external code and calibrate to 100 discrete head measurements, 3 time series head measurements, and 1 stream discharge time series within the model domain. Head measurements are going to be taken from the New York State Department of Conservation Water Wells program, and stream discharge will be taken from the USGS gauging station along the Buffalo River. So where we currently are is we're in the calibration period of calibrating to historical 2005 to 2015 data. Further calibration is really needed before we can really make confident assessments of groundwater quality and quantity issues under climate change. We see in Figure 2 just a preliminary result. This is hydrologic head results from the model on the time series, the last December 31st, 2049, the last day in my first future time series. So SWAT-MODFLOW will be able to output groundwater flux, hydrologic head, stream discharge, and stream stage in the future. We'll be able to assess all of these different components as time series as the system progresses over the course under changing climate. And then in the future, later we hope to include an RT3D model which will output nitrogen fluxes through the system. And that way we'll be able to assess nitrogen discharge from the watershed into Lake Erie. So I hope you guys enjoyed my talk. Thank you for listening, and I would appreciate any feedback that you guys have. Thanks.